All right, let's talk about three words you hear all the time in the tech world: encryption, hashing, and encoding. Now, they sound kind of similar, and honestly, they get mixed up constantly. But they are the invisible engines that make our digital lives possible. By the end of this, you're going to know exactly what each one does, why they're so different, and where you're using them every single day.
So let's start with a big question. Every time you send a message, log into a website, or, attach a photo to an email, you're basically counting on some system to keep that data private, to make sure nobody's messed with it, and to make sure it actually shows up in a way the other side can understand. Well, these three challenges, they're solved by our three key concepts. So, first up, the big one, secrecy. When you send information over the internet, it's not going through some private, sealed tube. Nope. It's hopping between all these different servers, and really, at any point, someone could be listening in. So how in the world do we keep our conversations private? Well, this threat has a name. Security experts call it a man-in-the-middle attack. It's exactly what it sounds like. Someone gets in the middle of your conversation. It's like someone grabbing your mail out of the mailbox, opening it, reading it, and then putting it back, and you'd never even know what happened.
And the solution to this snooping problem? That's where encryption comes in. This is our tool for confidentiality, for secrecy. The whole point is to take something anyone can read, like a message, and just scramble it into complete and utter gibberish. That way, even if someone intercepts it, it's totally useless to them.
This little diagram shows it perfectly. You start with your normal message, your plain text. Then you use a secret key. Think of it like a super complex password to lock it up and turn it into ciphertext. Now here's the magic part. The only way to turn that scrambled mess back into the original message is to have the exact right key to unlock it. No key, no message. Simple as that. And speaking of keys, there are basically two flavors. Symmetric is the straightforward one. You use the exact same secret key to both lock and unlock the data. Asymmetric is a little more clever. It uses a matched pair of keys. There's a public key you can give to anyone. It can only lock data, but the only thing that can unlock it is the other key in the pair, the private key, which you keep completely to yourself.
And you are using this stuff all the time. When WhatsApp tells you your messages are end-to-end encrypted, this is exactly what they're talking about. If you use a VPN, it's encrypting all your internet traffic. And if you encrypt a file on your computer, you're making sure that even if someone steals your laptop, your data is still just a bunch of unreadable junk. Okay, so we've got secrecy covered. But what about trust? How do you know the file you just downloaded hasn't been changed? And here's a good one. How can a website check your password is correct without actually storing your password? That would be a huge security risk. This is the problem of integrity. This quote right here, it hits the nail on the head. This is the single biggest difference between hashing and encryption. Hashing is a one-way street. You can't reverse it. The whole point is that you're not supposed to be able to get the original data back. So, our solution for integrity is hashing. Think of it like creating a unique digital fingerprint. You can feed anything into a hashing algorithm, one word, a whole movie, whatever, and it will always spit out a short, fixed-size string of letters and numbers. And if you change just one tiny bit of that original data, even a single comma, the fingerprint, the hash, changes completely. And the classic example is passwords. It's so clever. A good website never, ever stores your actual password. When you sign up, it takes your password, hashes it, and stores that unique fingerprint. Then, when you try to log in, it hashes the password you just typed in and just compares the two fingerprints. If they match, boom, you're in. The website verified it was you without ever needing to see your secret password. Now, for this to be secure, a good hash has to follow a few really strict rules. Collision resistance just means it's basically impossible for two different files to end up with the same fingerprint. Preimage resistance is that one-way property we talked about. You can't work backward from the fingerprint to figure out the original password. And second preimage resistance means that if I have a file and its fingerprint, I can't go find another file that has that exact same fingerprint. It's what makes this system trustworthy. All right, on to our final problem. And this one's a little different. It's not really about security, it's more about logistics. See, the internet was originally built to handle simple text. So how do we show things like images, videos, and complex files through systems that are only designed to understand letters and numbers? This is the problem of compatibility. And this quote just explains it perfectly. This is the aha moment for encoding. It's not about hiding anything. It's just about translating data so it doesn't get broken in transit.
Base 64 is the most famous example, and all it does is represent complex data using a safe, simple set of text characters. So, our third and final tool is encoding. You can think of it as a universal translator. And let's be super clear on this. The purpose is usability, not security. It's completely reversible, and there's no secret key. Anyone can decode it if they know the method being used. It provides literally zero security on its own. And you see encoding everywhere, working behind the scenes. Every time you attach a file to an email, a standard called MIME is probably using base 64 to turn that file into a giant block of text that can travel safely through email servers. You know the security certificates for websites? They're often stored in an encoded format so they can be easily copied and pasted. It is the hidden workhorse of just making things work. Okay, so we've got our three problems: secrecy, integrity, and compatibility. And we've got our three solutions. Now let's pull it all together and put them head to head so this really sticks. This right here is your ultimate cheat sheet. Let's run through it. Encryption. Its purpose is secrecy. It's reversible, but only if you have the key. Think secure messages. Hashing. Its purpose is integrity, making sure nothing's changed. It's irreversible, a one-way street. Think password verification. And finally, encoding. Its purpose is just compatibility. It's easily reversible by anyone, no key needed. Think sending email attachments. So if you walk away with nothing else, remember this right here. It's really that simple. If you need to keep a secret, you use encryption. If you need to prove something is authentic and hasn't been tampered with, you use hashing. And if you just need to make sure data can get from point A to point B without breaking, you use encoding. Secrecy, integrity, compatibility. And I'll leave you with a final thought. These tools aren't used in isolation. They actually work together all the time. A secure system might encode an attachment, then encrypt the whole package for secrecy, and use hashes to verify everything as authentic. So now that you know the difference, start looking for them. You will be amazed at how these three concepts are quietly working together 24/7 to secure your digital world.